Sorry for getting back to this so late. I totally messed up on the first one, realized it, and then I had to wait till I got home to redo the video. So anyway, here we go. And here we are at the cooling silver video. If you've had a chance to read this, great. If not, please pause the video and read it, and we'll get started. So basically what's happening here is we have something that is cooling. It was 70 degrees Celsius above room temperature initially, and now it's 60, and we're going to try to figure out, well, what's it going to be like in 15 minutes, what's the temperature going to be like in 2 hours, and then how long will it take for the silver ingot, or the ingot of silver, to cool down to 10 degrees Celsius above room temperature. So these kinds of problems are lend themselves to Newton's law of cooling. So Newton's law of cooling states that the rate, so dy dt, you can see the equation here, dy dt equals k times the quantity y minus y sub s. So what does that mean? Well, that just means that the rate at which y changes, okay, which is dy dt, the rate at which y changes with respect to t, and y, again, is up here. Y of t is a current temperature, or you could think of it as the temperature at time t. So the temperature right now is 60 degrees Celsius above room temperature, and so forth. So y is changing, the temperature of the object is changing, and y sub s, you can see right here, is the surrounding temperature. So the surrounding temperature is always going to remain constant in these problems, and so let me write that down as constant. So as soon as we find what that is, we can just put that into our formula. If you do the problem the way I'm going to show you how to do it, then you're going to probably run into less difficulty than if you try to read the book and try to figure out how the book teaches it. I've read a few books on this, and every time I see the way the book instructs this, it's really complicated because there's a lot of variables in there. So trying to break it down and make it easier, I don't like to try to remember these big long formulas. I like to remember the basics and then go from there. So the basics are, again, the rate at which Newton's law of cooling, yeah, it's the same Newton that has the 3 laws of motion. So Newton has also a law of cooling. It says that the rate at which an object's temperature is changing is proportional to the difference between the current temperature of the object and the surrounding temperature. Okay, so in this particular example, the surrounding temperature is room temperature. So we got to figure out what that is. Well, it could be anything. In fact, you could choose any value in this case for the room temperature. Now, normally you do a problem like this, it'll give you what the surrounding temperature is, but in this case, you get to just select any room temperature you want, and the easiest number that we could work with would be, we're going to just let the room temperature be equal to, let the surrounding temperature, or the room temperature, be equal to 0 degrees. I don't want to do any more work than I have to, so I'm going to let the surrounding temperature be 0 degrees. You could let it be 50, 60, 70, whatever you want. Actually, that wouldn't work very well, but anything less than the numbers we see here. But 0 degrees Celsius would be a good one, because then any number we get is just going to be the number of degrees above room temperature. And so if we let y sub s be equal to 0 degrees, then we can change our equation here to dy dt equals k times y minus 0. In other words, we have dy dt equals k times y. Now this is a really important equation, because what you should recognize here is, back when we very first started chapter 6, we said this kind of an equation is a differential equation. In fact, it's a special differential equation called a separable differential equation. And the separable part means that you can separate the variables. We have a dt and we have a dy. So we're going to multiply both sides by dt, and we're going to divide both sides by y. And what that does for us is, again, separates our variables. We see that the dt's cancel, the y's cancel over here, and we get on the left side, I'm going to write this like this so it might be easier for some of you guys to see that. this process here is the same process that I keep talking about. How you get a differential equation FRQ, and there's 5 points devoted to solving the differential equation, and then finding C, and then finding an initial value, and getting the particular solution to the initial value problem. And so, all that being said, this is a super important process. So anyway, make sure you know how to do this before next week's test, before the AP exam, before the semester 1 final, and then that's about it. So at this point, you should recognize that we really want to do, what we want to do is we want to find y. We want to find a function that we can use. We can find a function for y and plug in the values that we need to be able to plug in to find our answers. Okay, so we're going to go ahead and integrate both sides, and on the left side we know that the antiderivative of 1 over y dy is ln of the absolute value of y equals, now the antiderivative of k, since k is a constant, is just kt plus c. Okay, here we have a logarithmic equation. We've gone through all this. We have our variable wrapped up in our argument. We want to unwrap that or free it up, and we do that by converting this logarithmic equation, put the k there, logarithmic equation to an exponential equation. At this point, I could have taken those bars away from the y, because when I raise e to any number, that's going to produce a positive number. It's never going to be 0, never going to be negative, even. So take the bars away. In fact, let's take the bars away now. But at the same time, we're going to rewrite e. We're going to rewrite the left side, move it on the right, but we're going to write it as e to the kt times e to the c. Okay. And that, we're making use of a law of exponents that says, let's see, let's use some numbers. Let's say a to the x times a to the y. If we have the same base, then we just add the exponents. So that's the way we used to do that. Algebra 1, Algebra 2, pre-calc honors. But now we're going to go backwards. We start with the exponents added, and then we split it up so the base is the same, and we have each of those exponents in those positions, and just like we do here. So to remind you that here we have a constant, so that's constant, and we can call it anything we want. Well, we like c, so let's continue to call it c. So we have y equals c times e to the kt. Alright, so once we have that, we're almost there. We just have to now find what c is equal to. Okay, so if we remember what was going on in the beginning here, right now the temperature is 60 degrees above. Okay, so we're just going to call that 60 degrees. That's now. Okay, then, which was 20 minutes ago, it was 70 degrees Celsius above room temperature. Okay, well, we can manipulate these numbers here a little bit to fit our equation. In fact, it would be easier if we just said the then part is our y of 0. Okay, in other words, when t is 0, we're going to let the t equals 0 part be when the temperature was 70 degrees above, and then the 20 minutes later, which would be y of 20, we've got our temperature at 60 degrees above. So this is plus 20 minutes. Okay, and then, so if that's the case, we use that information to figure out what c is equal to. Okay, so let's do this in purple. Continue with purple. So we have y of 20 is equal to c times e to the k times 20, because t is 20, and that again is equal to 60 degrees. Okay, I totally blew it. I don't want to do that. I don't want to do that yet. Sorry, we're going to come back to that. Should I cross it off? We're going to bypass that. Sorry, jumped the gun there. Y of 0 is when t is 0. That's going to help us find our c. We need to do that first. So k times 0, and we said y of 0 is 70. I didn't want to rewind the video. We're already at almost 10 minutes. So that means k e to the 0 is 1, and so we have that c is 70. Okay, and so that gives us our equation. That gives us our function y of t equals 70 e to the k times t. Well, we have our equation here. Yeah, we have our c, but now we need our k. And that's where we're going to go back to this. Y of 20 is equal to 70 times e to the 20 being t times k, and that is equal to 60. Okay, so we take this part of the equation, and we're getting deep here in this problem. We take this part of the equation, solving for k. So k is our growth constant. K is the important number here that stays constant throughout this entire problem. It's going to help us figure out, well, how fast or slowly is the object going to cool. So if we divide both sides by 70, then we reduce the fraction, and we now have an exponential equation. We're solving for k. We need to convert to logs or take the log of both sides. So we get 20k equals ln of 6 over 7. And if we want to find k, we take ln of 6 over 7, divide that entire expression by 20. And I'm going to put a box around my k, and that right there is going to help us. Let me scoot this out a little bit so you can see what's going on. Almost done. And so therefore, it doesn't matter what k is. We're going to type that into the calculator and store it. Okay, so store it on, I usually store it in alpha A. If you need help with that, let me know. But we have our function now, and this is our bread and butter. Okay, so y of t equals 70 times e to the k t. And that k now with a box around it indicates to me that I've got that stored, and I can find all the information I need based on that equation right there. So I'm going to get to the next video here in just a moment.